solving general equations and what have you with complex numbers is nothing new really. It's just like algebra. So then the next type of equation that we really looked at were quadratic equations. But now, instead of, if you think about when the discriminant was less than 0, we went, oh, no answers. Now we can find answers. So I get a quadratic like this one. X squared plus 3x plus 7 is equal to 0. Doesn't factorise, so I go to my quadratic formula and I get the square root of negative 19. Let's say in the past, that's where we'd say, oh, well, there's no real solutions. And that's true. There are no real solutions. However, we can now simplify that third, because the square root of negative 19 is the same as saying square root of 19 times the square root of negative 1. Square root of negative 1 is I. And so we can now get the imaginary part to this solution. That was the bit we couldn't work out before, and why we said, well, there's no solutions. So negative 3 plus the square root of 19i, in this case I have written it all as one fraction over 2, and negative 3 minus the square root of 19i all over 2. The alternative way then to solving quadratics, what now means that every quadratic can be solved by completing the square. Because now every quadratic can be turned into the difference of two squares. X squared plus 3x plus 7. Well, if I complete the square, I would get x plus 3 on 2 all squared plus 19 on 4. Now previously that was a problem, because that's not the difference of two squares. But I can now make it the difference of two squares by, instead of writing it as plus 19 on 4, I write it as minus 19 on 4 I squared. And it's now the difference of two squares. And so I say, well, okay, well, that's going to be x plus 3 on 2 plus the square root of 19 on 2i, x plus 3 on 2 minus the square root of 19 on 2i, and then we solve that one and we get the same two answers. Now we couldn't do that before, because I guess, well, I'll say half, I don't know what the exact ratio is, but a half of all our quadratic equations couldn't be written as the difference of two squares, so it wasn't a great method. But now every quadratic can be written as a difference of two squares. If I want to create quadratics, and here's a really important fact, if in your quadratic all the coefficients are real numbers, then solutions will always appear in conjugate pairs. And that comes down to the quadratic formula, because the quadratic formula is going to go negative b plus or minus the square root. Now the imaginary part's always going to be associated with that plus or minus the square root. So you're going to have conjugates. So if I put it this way, if I factorise, we now know the solutions are in conjugate pairs. So one factor would be x minus z, the other factor would be x minus its conjugate. If I was to expand that out, we get x squared minus z plus z conjugate times x plus z times z conjugate. Well, z plus z conjugate, if you add the two conjugates together, the imaginary parts are going to cancel out. And so it actually doesn't matter that I don't know what the square root of minus 1 is, because it's going to disappear. I will always get twice whatever the real value is. So whatever the real part is. And then plus that, there's that thing again, z times z conjugate, which is x squared plus y squared, the sum of two squares. So now, if I'm told I've got these two roots, 4 plus I, 4 minus I, the long way about it would be actually to write it as x minus 4 plus I times x minus 4 minus I, expand the whole thing out. But it's a lot quicker if I go, hang on a sec, I know the sum of the roots, the imaginary parts are going to cancel. I'll get twice the real part, which is 8. Now you might not actually write this down, this might be a process in your head that you're going through. And the product of the roots, well, that's going to be the real part squared plus the imaginary part squared. So 4 squared plus 1 squared, 17. So my quadratic, x squared minus twice the real, minus 8, plus 17. There's the equation. Rather than wasting time expanding the whole thing out, collecting like terms and so on. Well, how do we find the square root of a complex number? Because if we're going to use the quadratic formula, yeah, that one before was nice. because we ended up with just one thing, square root of minus 19. We could do that, that was easy. But what happens if the complex number in there has a real and imaginary part? How do we find the square root? Now the first way, there's lots of ways of doing it. The first way is to go, well look, this first equation, a plus ib equals the square root of x minus iy. Too hard, not going to do it. I'll square both sides. That's easier. Because I can expand out a plus ib all squared. And I'll get a squared plus 2abi minus b squared. Because it would be plus I squared b squared, I squared's -1. But the real part must equal the real part, and the imaginary part must equal the imaginary part. So what I now know is this. The square root of x plus iy, it will give me an answer, a plus ib. A squared minus b squared will be the real part of what I'm square rooting. And 2ab will be the imaginary part of what I'm square rooting. Simultaneous equations, I can then work out the answer. So if I wanted to find the square root of -12 plus 16i, I can say, well, a squared minus b squared is -12. And so a squared minus b squared is the real part. 2ab is the imaginary part. It's easier to rearrange the right hand side there, so I'll make b equal 8 over a, sub it into the left hand side, and we just end up with well, it's actually a quartic, but it's a quartic we can treat like a quadratic. But this quadratic should be a bit easier to solve. It's in terms of a squared, multiply together to give -64, add together to give 12, which is -4 and 16. I've got a squared equals 4 or a squared equals -16. However, remember, a and b are real numbers. So a squared equals -16 is not going to give me part of the solution. Because if a squared equals -16, a will equal 4i. That's not real. I want a real answer. So it's the left hand side I'm interested in. And we get a is plus or minus 2. Therefore b will be plus or minus 4. Now, that actually is a bad way I've written that answer, because that actually implies there are 4 possibilities. What I am really meaning to say is when a is plus 2, b is plus 4. Because over here we know the signs are going to be the same. B is 8 on A. So my actual answer then, there it is, plus or minus 2 plus 4i. Here's the difference from when we were dealing with real numbers. If I said to you x squared is 16, you would give me an answer plus or minus 4. If I said to you x was the square root of 16, you would just give me the answer positive 4. Complex numbers are different. I'm simply saying the square root of -12 plus 16i. But how do I know whether the answer is plus 2 plus 4i or minus 2 plus 4i? Because they're not on the number line. I can't order them, so I don't know. So in this case, I do put both down. Some people will define the square root. If you're finding the positive square root, they'll define it as, well, the answer is when the real part is positive. So they would give the answer as 2 plus 4i for this one. That's fine, and if they define it that way in the question, then that's what we'll go with. But if they don't define it that way, my opinion anyway, is we have both plus or minus 2 plus 4i for that answer. A plus ib is the square root of x plus iy. Here's another way of looking at it. Okay, we just saw a squared minus b squared is x, 2ab is y. If I play around with that a little bit, x squared plus y squared, there's that lovely sum of two squares again. X squared plus y squared. If I expand that all out, sub in the a squared minus b squared and the 2ab, it actually turns out to be a4, a to the power 4, 2a squared b squared, b to the power 4. That's a perfect square. So in fact, I think that's a much nicer simultaneous equation to play with. A squared minus b squared is x. A squared plus b squared will always be the square root, and there it is again, the real part squared plus the imaginary part squared. Simultaneous solving that, Add them together, gets rid of the b squared. Subtract them, gets rid of the a squared. Very nice numbers to deal with. Now, how do you know? Because again, you're dealing with plus or minus on the squares. Turns out, if the imaginary part is positive, when you're finding the square roots, then the real and the imaginary part of the answer will have the same sign. Okay? If the imaginary part is negative, they'll have a different sign. So let's look at that same question. So that same question, a squared minus b squared is negative 12. A squared plus b squared will be the square root of the imaginary part squared plus the real part squared. Well, 12 squared is 144. 16 squared is 256, is that right? 256. Add them together, we get 400. Square root of 400 is 20. All right, there's my simultaneous equation. I got 2a squared is 8. A is 2. I'm just going to take the positive part here. So a is 2. And then I can sub back in, I get b is 4. Remember? The imaginary part was positive, so I knew they had the same sign. The reason I didn't worry about the plus or minus here is because I put it in my final answer. So there we get it. Plus or minus 2 plus 4i. Heck of a lot quicker than the other method. Okay? Because the numbers were nice, I'll be honest with you. 12 and 16 are beautiful numbers. 12 and 16 are the two pieces that go together to form a special triplet of numbers. Do we know what triplet of numbers I'm talking about? It's got a name. It's what we call a Pythagorean Triad. If these two numbers are the two smaller numbers of a Pythagorean Triad, this method is going to be easy. Say Pythagorean Triads. The very first one, the most common one, is the one that goes 3, 4, 5. So if I saw 3 plus 4i here, I know, well, going to be a piece of cake to work that one out. What's another one? 5, 12, 13. Is that one? 5, 12, 13? Or is it 5, 6? Yeah. 5, 12, 13. So those sorts of numbers work out nice. Let me show you one where those sorts of numbers don't work out that nice. 4 and 5 are not two numbers that then go and make up a nice, neat Pythagorean triad. Now the technique still works, but here's what happens. Okay, a squared minus b squared is 5, that's fine. But it doesn't turn out to be a nice, neat whole number because it's not a Pythagorean triad. I don't go a squared plus b squared and I get a nice, neat something that I can find the square root of. So it's the square root of 41. So simultaneously now, I get, well, 2a squared is 5 plus the square root of 41. So a squared is a half of 5 plus the square root of 41. A is a half of root 10 plus 2 root 41. And then I could work out b squared by doing simultaneous equations again, or substitute in, which way you prefer. And I get b as a half of the square root of negative 10 plus 2 root 41. Now the imaginary part was negative, so they'll have different signs. There's my answer. The square root of 5 minus 4i plus or minus a half root 10 plus 2 root 41 minus I root negative 10 plus 2 root 41. Now, the other method, it's still not going to give you nice, neat numbers, the other method, but it might do it a little bit easier than this one. So it just depends on the numbers, which way you go. Coefficients aren't always real. So I could go and get a quadratic equation where the coefficients are also complex numbers. But the quadratic formula doesn't change. Z equals negative b plus or minus the square root of b squared minus 4ac. Tidying up under the square root sign. Oh, look at that. 5 and 12. Thank you very much. 5 and 12. I know this one will work out nicely. So just on the right hand side, I'll work out what the square root is. So square roots, a squared minus b squared will give me the real part. A squared plus b squared, well, the Pythagorean triad, 5, 12, 13. Solve them simultaneously. I've got a is 2, That makes b equal to 3. Back to my quadratic formula. The imaginary part is positive, so therefore I know they have the same sign. So it's plus or minus 2 plus 3i. And, well, finishing that off, I get a solution of I, or negative 2 minus 2i. So you see, if you happen to fall upon a Pythagorean triad, that method for finding the square root is very quick. Very quick. So let's play with some quadratics.